Guys, we are now trying to derive the second part of the equation. The second part of the equation is trying to relate m by I to any of this. So basically we are trying to relate this so that we can relate to E by ER also. So what I am trying to do is that I am taking the cross section of the beam like this. Here the cross section I am trying to draw it in a bigger way here. So all these fibers above will experience compressive stresses, all the fibers below will experience the tensile stresses. I am considering one such fiber which has an element dA. That fiber is at the distance y from the neutral axis and that will experience a stress sigma b. What is the formula for sigma, guys? So what is stress? What is the formula for stress? What is stress basically? Stress is force by area. Force by area. So you can definitely say that if this is a stress for this element, this is the force on this element divided by the area of this element. So I want to use this equation for this element. What is the stress in this element? So now the stress in this element is sigma b. What is the force on the element? Fn. Fn stands for normal stress. Normal means perpendicular anta. ಇದಕ್ಕೆ perpendicular ಆಗಿರುತ್ತೆ ಅಂತ. ಇದಕ್ಕೆ ಈ ತರ perpendicular ಆಗಿರುತ್ತೆ. Fn divided by area. ಇದರ area ಎಷ್ಟು ಎಲಿಮೆಂಟ್ ಇದು? dA. Okay? And then we already know that now I can actually write this as Fn equal to, I can actually rearrange this equation. Then write this equation as Fn is equal to sigma b into dA. Sigma b into dA. And then we already know from the previous derivation, this part of the derivation we have already derived. So we know that from this part of the equation, we know that sigma b is nothing but y into E by R. So y into E by R. So we are trying to use this part of the equation here. So you can say that so this will become y into ER divided ER into dA. ER into dA. So this is the force Fn, and you know that moment is always force into distance. Moment created by this element is actually force multiplied by force Fn multiplied by this distance y. So you can always say that moment is equal to force into distance. Okay. It is as good as torque. Torque is equal to force into radius. Like that, moment is equal to force into distance. So same thing I am trying to do. So moment m for this element can be written as Fn into y, because this distance is nothing but y. Distance force ಎಲ್ಲ ಆಗ್ತದೆ ಈ ಎಲಿಮೆಂಟ್ ಮೇಲೆ. ಈ ಎಲಿಮೆಂಟ್ ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ? y ಎಷ್ಟು ದೂರದಲ್ಲಿದೆ. ಸೊ ಮೊಮೆಂಟ್ ಎಷ್ಟು ಕ್ರಿಯೇಟ್ ಆಯಿತು? ಫೋರ್ಸ್ ಫ್ರಮ್ ದಿ ಎಲಿಮೆಂಟ್ ಮಲ್ಟಿಪ್ಲೈಡ್ ಬೈ ದ ಡಿಸ್ಟೆನ್ಸ್ ಫ್ರಮ್ ದಿ ನ್ಯೂಟ್ರಲ್ ಆಕ್ಸಿಸ್. ಅಷ್ಟು ಮೊಮೆಂಟ್ ಕ್ರಿಯೇಟ್ ಆಯಿತು. ಸೊ ಮೊಮೆಂಟ್ ಈಸ್ ಆಕ್ಚುಲಿ ಗಿವನ್ ಬೈ m, but we call this as dm because this is for this element. It is not for the whole beam. Since this moment is for this element, we are calling this as differential moment. We will not call this as whole moment. Okay? So differential moment is actually Fn on this element multiplied by y for this element. So Fn is already like this. So we can say that dm is equal to, so you can substitute this value here. You can substitute this whole value of this here, and what do you get here? Y square into E by R into dA. if you want the complete moment, then you should integrate the moment of all these elements throughout. ಇದೆಲ್ಲ ಮೊಮೆಂಟ್ಗಳನ್ನ ಈ ಎಲಿಮೆಂಟ್ ಮಲ್ಟಿಪ್ಲೈ ಬೈ ದಿಸ್ y, ಈ ಎಲಿಮೆಂಟ್ ಮಲ್ಟಿಪ್ಲೈ ಬೈ ದಿಸ್ y, ಈ ಎಲಿಮೆಂಟ್ ಮಲ್ಟಿಪ್ಲೈ ದಿಸ್ y. If you want that, then you actually do integration. Okay, so you actually integrate this to get m. If you integrate this above equation, you get m. So if you integrate this, what you have is y square into e by r into dA. Y square into e by r into dA. Okay, guys, you can only integrate the variables but not the constants. You know what are constants in this? Young's modulus is the property of the material, like 200 GPa, 250 GPa or something. So it is constant. You can't integrate this because it is not varying with respect to this distance. And r is the radius of the beam at which it is bent. So these two are actually constants. So you can't integrate constants. So this has to be brought out of this here. So you can call this as m is equal to integration of dm, which is actually m is equal to y square dA. I'll write this equation anyhow. Y square dA into e by r. I'll write this as, and this, since this e by r is constant, I'll bring it here. So m is equal to e by r into integral of y square dA. And now this term y square dA, we call this as moment of inertia, because this depends on the shape of this beam, the shape of the cross section of the beam. So this equation can be written as m is equal to e by r into I, where this integration of y square dA is nothing but moment of inertia. Okay, so this can be written as m by I is equal to e by r, and we already know that e by r, we know that sigma b by y is equal to e by r already. So therefore, comparing this equation, we can write the final equation m by I is equal to sigma b by y is equal to e by r. Guys, basically you may be wondering why I actually made this into I. So I is actually integral of y square dA. So that actually depends on the shape of the beam, whether it is, whether this beam is a rectangular beam. And if you do y square dA, integral of y square dA for this rectangular beam, you get I is equal to b dq by 12. If you try to integrate all these areas now with respect to y, and integrate from 0 to y by 2, 0 to y, where this is from plus d by 2 to minus d by 2, and keeping this breadth as same, you get this formula. You finally get this answer as I is equal to b dq by 12 for rectangular section. Rectangular section madre ee tara barutte. If you try to do this integration for y square dA for circular sections alli pratiyondu element go y square into area. If you try to do it through integration, you get I is equal to n formula gottalla nimge. I for circular sections pi d to the power of 4 divided by 64. Jp is 32. Jp is sum of the moment of inertia in x-axis and y-axis, that is pi d to the power of 4 divided by 32. Like this, if you try to integrate y square dA for different sections, you get different formulas. So this is actually called as I. So we have actually tried to relate bending moment, bending stress, Young's modulus, moment of inertia, and radius of curvature.